hope you're ready. I got some RRT dances to do today. I killed my bike on the way in. I had to finally admit that it was time for service on my bike. I had taken it through the winter and it was just not working very well. And when I take it to the shop, I said, the steering's not working that well. And I go like this and move the handlebars away, and it was like I just excavated it from an Egyptian tomb or something. It was just sand coming out of the fork, the bearing in the fork, and he's like, ugh. It was a rough morning. Okay, let's do it. So last time we started talking about more global or complete approaches to motion planning, right? And the basic objective there was, if I have, if I'm given X, some initial condition of the system, some model of the system, of course, some goal state, potentially some objective function that I want to minimize, then I'd like to have, we talked about ways to write motion planners that will have the property that if it's possible to get from the start to the goal, they will find a solution. And if there's an objective function we talked about in the mixed integer case, possibly getting something that will find the optimal solution against some cost function. So that's a very powerful set of tools for your toolbox, but it's not quite enough to, let's say, stabilize a humanoid or somehow solve some of the more complicated feedback type design problems that we've been talking about. So in particular, let's see what happens if I try to generalize the question a little bit. So I guess I didn't finish here. Potentially an optimal path. So I want to start by generalizing the question. If we think about our ideas of stabilizing the pendulum at the upright, or any of the problems we've really looked at stabilizing a humanoid, the question that we tend to like to ask is, given some goal, can I find a solution that works for any initial condition, right? So I want to broaden, just instead of having a particular initial condition, somehow for all X initial conditions. What can we do about that? So, given we have some of these tools already, there's a couple obvious things you can try to do, right? One approach would be, if you can plan fast enough, we talked about doing planning as a way to do feedback control, right? And fast, depending on the time constant of your dynamics in your robot, right? Might have to be a kilohertz, and that's hard, maybe, but maybe you can get away with a lower update rate. If planning is fast, then the planner becomes a controller. That's the model predictive control idea. Which says, take whatever my current estimate of my state is and find a path from the start to the goal, get my planner, take the first step, then repeat. You'd like to also have properties, for instance, about it being the plans that come out being somehow consistent over time. You don't want them to have completely different plans coming out at every time. But roughly, if your planner is fast enough, then you do have a feedback policy. But the types of planners we talked about recently probably aren't fast enough. So that's not quite enough. The RRT idea does permit sort of a nice idea here. There's sort of an idea that I want to start with here that sort of extends naturally from what we talked about last time, the rapidly exploring random trees, right? What if we build the RRT backwards from the goal? And as we start growing our tree by picking random samples and extending towards those samples, right, we will have effectively been computing plans for more and more possible initial conditions, right? Every one of these nodes is an initial condition for which we already have a plan computed that will get me back to the goal. Okay? So if there's some finite set of initial conditions that I care about, then maybe if I've somehow covered this space sufficiently, I've got something that looks like a feedback controller. Now, since this is a set of finite measure, then my real initial condition when I'm running is not going to be exactly at one of those nodes, but maybe the problem of just connecting to a local branch, if there's enough local branches, is simple enough that you could do that on the fly, and then you have a feedback policy that comes out of your RRT. That's pretty cool. And there are generalizations of randomized motion planners. In fact, the history is sort of backwards, but the roadmaps came first. But there are versions of this where you build an undirected graph that can get you from any start to any goal. That would be called a probabilistic roadmap. But this idea for sort of stabilizing a goal in state space, I think this is a very nice picture, very appealing picture to say, if I've done enough planning and my objective was just to cover the space, then I've got roughly a feedback controller. People don't really do that for tasks that have dynamics in them, and we could ask why. I think some of the reasons are fairly subtle, but I don't consider this the solution yet. And let me see if I can convince you. I think there's a couple problems with this. Let's say limitations. This whole idea puts a very high premium on having a state estimate, right? So somehow, just needing to know exactly where I am in the high-dimensional space or whatever in order to follow a plan, it requires a state estimate. That's a problem with a lot of the methods we talk about, so I don't want to fault this one in particular, but it's certainly true here. But what's even more true is that I don't really have a way to think about if the policy, if the feedback controller is represented like this, then I don't have a good way to think about the robustness of this controller to things like state estimation uncertainty, model uncertainty, and some of the other things that we were able to do when our controller was a linear feedback and our plant was a pendulum. We had some pretty good tools for thinking about robustness and thinking about model uncertainty, and we'll develop even more of them next week. So this representation, I don't really know how to answer those kind of questions with. And I mean that in sort of a deep way, I think. So this has got the notion of trajectories so baked in that it's maybe fundamentally hard to think about robustness in this context. Because let's say I planned all this given my pendulum had mass 3, right? And I find out later it's got mass 3.2. Okay? Then this trajectory may not be feasible for the pendulum with mass 3.2. So if I were to, the very notion of a trajectory is a particular solution through state space. And the modified system, that might not be a realizable trajectory for the modified system, right? A feedback controller, I can ask, how does it perform given the model parameters are different? Because there's a defined action for every initial state. But if somehow my entire premise, my entire path is now invalid because my model changed, then how do you ask questions about robustness? Right? It's not just that the representation of this is hard to think about, it's that somehow it's baked in this notion of a feasible trajectory that may not be valid if the model changes, right? Did you have a question?
Yeah, wouldn't the RRT not require a full state estimate of whatever state is required to be in the goal? Like if your robot has X, Y, Z, and you don't actually care what the V is, but you care about your X and Y, then you should be able to create the RRT just based off of the X and Y.
If your rules of how do you advance from one state to the other depend on that dynamic, then it has to be here, right? So I think the only general answer is that you do need the full state feedback. You can come up with weird cases like, so if I have a robot over here and a robot over there and they're completely independent, and I wrote the model that had both, then there's no coupling and you could write a separation, but that's true of any of our feedback design principles, right? I think you cannot project or slice through state space in general if the dynamics are coupled across those. Yes?
So I agree in the traditional RRT is going from point to point and edge is just a path segment. But if you generalize the node to represent like a region of configuration space, and then your edge is this concept that it can go from a region to a region, and it's robust, then it seems like you could talk about some robustness. I don't know what the formal guarantees would be, but you can think about robustness in this concept of RRT.
So that's the idea of feedback motion planning, and that's exactly where we're going. Good call.
Sorry.
No, that's good. That's good. So it's how do you take this idea and what tools do we have to actually implement that idea of turning these into regions instead of I think the line is fundamentally fragile, and we have to somehow generalize it. But we actually have all the tools we need to do that well, and that's the goal for today. So right on. I agree. Any other questions? Cool. There's also questions about how would you smooth from all initial conditions. There's a bunch of things that if you actually go to implement something like this, you don't want to do the RRT dance from every initial condition, right? But you could imagine ways like the RRT star, which tries to find optimal solutions, would slowly smooth this out. There are ways to get around these, but at some point, we need something more, I think. And I do think the fundamental fragility is just this notion that the vocabulary is wrong, I think. Somehow the vocabulary of using trajectories in state space is the simple and natural one. It works well for planning. We know how to write optimizations around it, but it's somehow not the right vocabulary for talking about feedback and robustness. Okay, so how do we generalize that to not trajectories but regions? Okay, and let me say it from a different perspective. So from a practical perspective, I have a chair in the middle of my workspace. So imagine you're Boston Dynamics, right? So and you've spent years writing really, really good controllers that make the robot trot and walk and bound and gallop, right? And they have really big regions of attraction, right? Like they're just very robust, and you can kick the robot and all this. And now you need to do some new task, right? And some MIT graduate just got the new job. He says, "Oh, I've got the solution for it. You just build an RRT from the goal, and and stabilize trajectories." They're going to look at you like you're crazy. I'm not going to throw away years of rock solid engineering of level controllers that work really, really well, and somehow replace that with a policy that was designed like this, right? So, a lot of times we actually have low-level feedback controllers, or let me call them local feedback controllers. That work really well. Okay, and they solve away a lot of the problems that are the sort of the pitfalls of this, right? So somehow the low-level controllers will be robust to the sensor noise, and they've been tuned in, and you don't just throw that kind of stuff away. Same thing for manipulation. You can imagine writing even by hand a grasping controller or something, or primitives that push or slide or do other things for manipulation, and you don't want to throw all that stuff away just to do a planning. But you'd like to be able to ask for a new task. How can I recycle my low-level feedback controllers into something that's a coherent plan that is robust to noise and uncertainty for this new task, right? In fact, one of the initial motivations for motion planning was a famous paper by Lozano Perez and Matt Mason and Taylor. It's the LMT paper, Lozano, Mason, Taylor, that talks about peg and hole insertion, okay, which is a manipulation problem. And it talks about sort of these guarded moves of how do you go down and touch the edge of the peg in order to sort of insert robustly, and it introduced this idea of if I were to do this move, there's a set of initial conditions from which this move would actually accomplish some task. That's the pre-image of that move. And if I can sort of back chain the pre-images of all of these potentially guarded moves, then I can somehow figure out what I should do from every initial condition. And this is a famous classic paper now that was about manipulation, but it was building up this idea of how do I compose not trajectories, but pre-images of if I were to take this set of actions for some amount of time, it's going to work for a large set of initial conditions, for regions, okay? But somehow we lost that in the trajectory world, where trajectory optimization works well and randomized motion planning works well. And so how do we get it back and do feedback motion planning? These are a little abstract, and even my peg and hole was just with a chalk in the air. But I want to make it concrete with the particular model system that Dan Kodacek and company used to sort of introduce the pictures that I like the most about feedback motion planning to the world. And that was a set of experiments and papers on juggling robots. If you look at the history, or if you talk to the authors about how the juggling robots got started, it was actually Dan Kodacek was fascinated with Raybert's hoppers, and he was he wanted to start understanding. So Mark Raybert said things like, you put a constant amount of energy in on every push, and you can achieve a stable hopping height. And Dan was trying to say, can I prove that? Can I understand the sort of things behind that? And he was boiling the hopping models down to their simplest possible model systems. And he is also the one who came up with the slip, or one of the people that contributed to the slip model we talked about, the spring-loaded inverted pendulum. But the offshoot from this was also a set of juggling robots that were effectively, almost like a hopping robot, but now it's a paddle bouncing a center of mass up where the ground is moving instead of the robots moving. And he started building robots that were sort of trying to understand Raybert's ideas, maybe, but in the context of juggling. And then they got more fancy too. They could do juggling tricks. But the simplest model of a juggler is actually the one-dimensional juggler. Is you have a ball here. It's only going to move up and down. And you have a paddle here that's moving up and down. Okay. We'll have some nominal position here. Call this the position of the paddle. This is the position of the ball. Okay. So my state space starts off as the ball, the paddle, the ball dot, and I'll assume that I have enough control authority to just command the velocity of the paddle. Got some big robot moving it up and down. And the task, much like hopping in place, the first task you do with juggling is you just try to stabilize a single ball on a periodic solution. Right? So I want to stabilize the hopping height, juggling height of the ball. Okay. Okay, so it turns out, that's a high-dimensional state space. Lots of interesting things can happen to the ball, even though it's restricted to one dimension. Everything gets easier. The analysis gets easier. The control design gets easier if you impose a simple, you impose something on your controller, and it'll flatten out the state space. And this big idea is called the mirror law. The low-level feedback controller was, I'm going to make my paddle height be basically the opposite of the ball height with some scale. Okay, you can achieve that via commanding R dot with some stabilization, right? So why is that a magically good idea? So first of all, it seems reasonable, right, to sort of have the ball go away, right? But if you do it actually like this as a linear function, then the collision between the ball and the paddle always happens at 0. That's nice. So if I want to go to write the Poincare map, initially I'm faced with a three-dimensional state space, two-dimensional map. But things collapse down if I know that the Poincare map is going to hit always at the same time. So of course, also b dot less than 0. And so I have a one-dimensional Poincare map, okay? And for any reasonable choice of k, you can draw the Poincare map of b dot at the nth impact to b dot at the n plus 1th impact. And you get something that looks like this, with a nice stable fixed point. And the unstable fixed point is just at the origin. Right, so if problem with the mirror law is it doesn't get started very well. If the ball's sitting on the paddle, it's stuck. But as soon as it moves a little bit away, it'll bounce up, add energy, and go to a stable hopping height. Okay? I mean, that's not obvious. You have to think about the mechanics of the aerial phase and everything like this. It's not obvious that a linear thing will actually stabilize a fixed height, but it works out. It's beautiful, and the equations are pretty simple. So this is an essentially globally stable feedback controller for bouncing a single paddle, one-dimensional hopper. The beautiful thing is that you can start extending this pretty quickly. Okay, so I'm going to extend it to 2D. Now I've got a paddle, okay, with a rotary joint and a ball. And I'd like to stabilize a periodic solution of the ball both vertically and horizontally, right? So I've got now X and Y position of the ball. Turns out the same mirror law idea can stabilize this. If I impose this to match, that stabilizes the Y dimension. And if I want to stabilize X, then the trick is to just impose one extra term. If you hit a little bit early, before it comes all the way down, then you'll move it this way. If you hit a little bit, before the paddle comes back up, then it'll move a little bit this way. And again, a very simple mirror law can stabilize the two-dimensional. Okay, and then if you separate out the two horizontal axes, then you can stabilize a three-dimensional juggler, and you end up with this series of experiments. You can also interleave two balls and all kinds of stuff. So this is the 2D juggler. The way to make a juggler, by the way, is to put you can of course do it in the vertical plane, but if you want to do it a two-dimensional juggler and not have the ball disappear to the side, then you put it on an air hockey table and put the air hockey table almost vertical. So yeah. Here's the 3D version. Right, just putting in two mirror laws allows you to juggle two balls, right? This was actually my first desk as an undergraduate researcher was roughly on the other side of that curtain. I don't think I was ever allowed on this side of the curtain, but that was done in the basement of the University of Michigan AI lab when I was a student. Okay, but then they started, so they had the basic juggling down, and that was cool, and that was sort of the, maybe motivated a little bit by the Raybert hoppers, but now you're doing juggling, and you should be able to do a lot more than that. So, I know one of the students that came and worked on this later, he could juggle like 15 balls or something like this, and they wanted to push the limits of this. So they started adding more and more behaviors to this. They could have it palm the ball like this, okay, which is just a variation on the mirror law. They had it so they could start up from stopped. They had tricks where they could go under a beam or over a beam, which is kind of like, under your leg or whatever. And you could just, any sort of small changes on these basic mirror laws allowed them to write really good feedback controllers that worked for a bunch of different variations of the juggling task. Okay, so this setup now motivated them to say, I've got all these feedback controllers that work well locally, but I'd like to now put together a juggling composition, and how do I then use those local feedback controllers to solve the bigger problem? And they did a really nice paper, which I like to show right from the paper here. Sequential composition of dynamically dexterous robot behaviors. Rob Burridge, Al Rizzi. Al's now at Boston Dynamics, and Dan Kodacek. Dan's now at Penn. And in that paper, they gave these pictures that I think are really formative, okay? So the Lyapunov function is a funnel. That's, you guys have been doing that for weeks now, but this was this idea that the way to think about a feedback controller is something that takes a set of initial conditions that's maybe potentially large and drives it to a set of initial conditions, or final conditions that are smaller. A stabilizing feedback controller should have that property. And the idea that you could describe that set as the level sets of a Lyapunov function was a big idea, I think. Says that if this is a good way to think about feedback control as having some controller that takes some set of initial conditions and drives it to a smaller set, then can't we do something like sequential composition of those controllers? If my goal is to stabilize the initial condition from the goal from a large range of initial conditions, maybe these are all the possible configurations that are stabilizable to the goal, then can I achieve that by composing feedback controllers so that one dumps into the next dumps into this, and now the region of attraction of my composed controller is somehow the image of all of those funnels projected down on the state space. And the dream is that you start filling the space with these funnels, right? So that was very motivational to me, and a lot of people, I think. If you ask Kodacek, about who came up with the idea for the funnels, he said, I don't know, Matt Mason. And then Matt Mason says, I don't know, someone else. So there's no, and there's a long sort of history of this idea in various forms, but this is the paper I feel like that captured it and drew those pictures the way that really made a big difference. So they did that, and that's how they made these little juggling compositions. But they didn't actually have all the tools when they wrote that paper to do what we can do today, right? So the way that they computed the region of they had a Lyapunov function, that there was just a Lyapunov candidate that they got from first principles thinking about mirror laws. But then how do they estimate the region of attraction of that? They did brute force experiments and samples, and they made plots, which I think I could find probably later in here. Scatter plots that said, our region of attraction is roughly this, right? Right, and that's, every one of those dots is a hard-earned experiment, right? And who knows if it's right? Do you take an inner approximation of those dots or an outer approximation, or what do you do? How do you use those? So now we can use sums of squares, right? And that was the reason I started looking at sums of squares a number of years ago, was to try to close the gap between this picture and trying to actually do feedback motion planning. So we're in a better place now. We can, at least for some models, we can do sums of squares to compute these regions of attraction. But there's other limitations too, right? So they didn't really have the motion planning ideas that were, like the RRT type ideas of filling the space weren't available then, right? So they weren't able to give us a sort of a powerful set of tools for saying, okay, if you have a bunch of controllers that are parameterized, how do you then reliably fill the space with those controllers? What they could do would be, I'm going to just instantiate this controller with k equals 5, k equals 6, k equals 7. And that comes up with some controller which has some region of attraction, hard-earned experiments that has something like this. And if I do that enough, maybe I've covered the space. But that's not what you really want. You'd like to somehow have a space-filling algorithm that says, okay, there's no controller that works in this part of space yet. How do I make a new controller? How do I find parameters of my controller that fill that part of space? And so there's additional tools that you have to put together. All right, so that's what we want to do now. So the proposal here, is the motivation clear? That's a big idea, I feel. That's going from trajectory motion planning to feedback motion planning. Cool. So, so here's the proposal, right? First proposal. Let's use sums of squares. To compute the regions of attraction. And given the toolkit, I mean, this lecture is kind of fun to give because it takes all the pieces that we've talked about throughout the term and it puts them all together in a single, in a single algorithm, I guess. So we could use sums of squares to compute the regions of attraction. We could also, for a relatively arbitrary system, we have a recipe for coming up with local controllers, right? We can use trajectory optimization plus LQR feedback, time varying, let's say. For local controllers. Okay, now that gives us a step up on the older approach. If we're willing to do this, then there's no cleverness required to come up with the feedback controllers, but if you have been clever and you have a good controller for trotting on Big Dog or whatever, you should use it. But this has the nice property that, for a particular initial condition, I could do trajectory optimization in LQR and come up with a local controller that works in whatever part of state space I want, and it works for most arbitrary systems, right? So how to play out on, for instance, the pendulum. Right, so this is my state space of my pendulum. That's my upright configuration. The gray region is the region of attraction of the LQR controller at the pendulum. And now I'd like to think about adding a new funnel, right? So what if I wanted to say I want a controller that goes from 0 and lands in the end in the final time, then I can do trajectory optimization to swing up from the bottom to the top. I can stabilize that with a time varying feedback controller, right? And that's the same picture that Burge drew, but now this gray region from around the initial condition up is the region of attraction of a time varying controller, which has as its final condition the region of attraction of the LQR of the time invariant controller, right? So the sums of squares analysis has some additional criteria required, right? So we talked about that you can have a time-varying Lyapunov function, right? But so far, the word region of attraction is restricted to this notion of stability, which the trajectory is not stable. It's a finite duration object, right? So what does it mean to have a Lyapunov function for a finite time operation? Well, I can still have some function which has the property that I'm going to define the funnel as a sublevel set. Some variable rho of t, let's say. And I'd like to make sure that the sub-level set of, I have final conditions where the sub-level set at the end of the trajectory had now better live inside the initial conditions of the region of attraction for the final, for the funnel I'm dumping into, right? So this picture of a funnel going like this into another funnel, if this is a final time, finite time trajectory, then this condition here says that the set v of x t final less than or equal to rho t final had better be inside the set of my v2 of x. In the case in the case I've drawn so far, this is not time varying it's dumping into, but it's also, it could be time varying too. Okay? And then I have the dynamic conditions which say that along inside the time, from time t0 to t final, I'd like v dot to be less than 0. Or all the variations we've talked about. Okay? So having that final exit condition allows me to say something about stability in the sense of this finite time operation. It allows me to combine finite time trajectories into a region of attraction of a bigger controller. Ultimately, you could think about the infinite horizon thing that's stable as that trajectory that goes to a fixed point, and therefore the trajectory is defined for all time. Okay? Now, back when I was doing this, I had trouble explaining the idea to people, so I made this animation. Yay! That took a really long time to make, 10 years ago or something. Okay, so we know that we can do this for lots of different systems. We could do it for quad rotors with 12 states. We can do it up to a relatively large number of states. The simplest proposal is to use LQR feedback along controllers, but you can also do the same thing to try to do better control design. There's no reason to restrict yourselves to LQR, and we did a bunch of experiments on the Acrobat to use sums of squares control design, where you explicitly iterate with your objective function being to maximize the region of attraction of the initial set of the controller. You could optimize over the control gains. You use LQR as your initial guess, and then change the control gains k in order to maximize the region of attraction. Okay, and that made the difference between having small LQR basins at the top for the Acrobat, which is that little blue region, into bigger ones, which is the big red ones, and along trajectories, the trajectories got a lot bigger too. Okay. Now, how do you put it all together now? So the second part that I was sort of missing from the Burridge work was a recipe for filling out space. But RRT roughly gives us that recipe, right? So the idea of having space filling by sampling, rejection sampling and then growing out a tree fits pretty nicely if you're able to make these funnels using trajectory optimization and local feedback stabilization. So here's sort of the proposal for combining motion planning with sums of squares and trajectory optimization for the pendulum. Okay, so you got your initial condition at the end. You pick a random initial you sample randomly across the state space. If the sample lands inside a gray region that was already covered by your controller, you can throw that one away. You don't need that. Keep sampling until you end up in the free space. When you do end up in the free space, do trajectory optimization to try to get you back to the tree. Right now the tree was initially just the point at the upright. The trajectory optimization may fail because it's not a global method, but when it succeeds, you add that trajectory to your tree. You compute the LQR controller around the tree. You add compute the regions of attraction, and now you add this gray region to your state space. Yeah.
When you're trying to do the trajectory optimization to get back to the tree? Do you just have to end up somewhere in the gray region?
No. That's very tempting, but the requirement is actually that you end up back at some node in the tree. So there's a skeleton inside the funnels, and the specific requirement is you end up at one of the nodes inside there, and that's for a number of reasons, but the simplest one is to think about having sort of continuity of this point I was making of having an infinite horizon trajectory, but you also want the controllers to sort of lead into each other. If you ended up right at the edge, you wouldn't know how to have a smooth controller along the transition. Good question. Okay, now I'll sample again, discarding samples in any of the gray regions, right? And every time I get one, I add a new trajectory, add the LQR controller, fill the space, okay? Now we have a proposal which will take random initial conditions, try to fill in specifically cover that initial condition with a local controller, and we'll eventually fill the space. Yeah.
How do you know which node on the tree to aim for with the trajectory?
Good. So we can get into arbitrary levels there's a bunch of details here. So this is different than the RRT in the sense that the RRT banks on the fact that there's only a local, eventually it will sample close enough to the tree that a trivial extend operation will work, okay? So you can get away with even having Euclidean distance metric and trivial extend operations which just go forward. That is no longer true here because my samples will always be outside some funnel, okay? So the trajectory optimization has to get from some point over some non-trivial distance to touch back to the tree. But you can write a final constraint, you can write your trajectory optimization as minimizing the cost function over time, subject to a final tree constraint, okay? So you say the cost or the constraint on the final state is that it is touching one of the nodes of that tree. That's not a differentiable constraint, because as it moves between So think about the problem of, I've got some trajectory optimization, and I just say that it has to land, it actually doesn't even have to land on a node of the tree, it could land in any of the continuous segments, right? So the distance between this and the tree is something you can imagine writing the distance function down, right? That distance is going to be discontinuous along the Voronoi regions. It'll be non-smooth across the Voronoi regions. So trajectory optimization could struggle with that. It'll get stuck in local minima and the like. But it has this property that now the trajectory optimization even if your distance metric is not very good, the trajectory optimization has the ability to find a feasible connection to the tree. Yeah. And that turned out to be essential to make the algorithm work. So the problem that we were talking about the other day of having a bad distance metric, if I say, here's my random sample, and it says, here's the closest point, try to grow towards that, you can use that as an initial guess for your trajectory optimization. But if the dynamics have a flow in this direction, the trajectory optimization seeded like this will eventually connect somewhere that's feasible. So even if you're just doing trajectory motion planning for an underactuated system, this is one of the things that I would have recommended in the sort of laundry list of things you can possibly do to make it work better for underactuated systems is using trajectory optimization to connect. It's just expensive, but it works well. It'll overcome the dynamic constraints. Okay, but for LQR trees, for this algorithm, it becomes essential to use trajectory optimization because you have to connect over a non-trivial distance.
So going to any point along the tree seems like the core constraint. Does that mean that these are sort of mixed integer problems, not so much linear?
You could potentially do better by explicitly telling it that there's a combinatorial choice. But the same way we did in trajectory optimization, we can do trajectory optimization through contact by just giving the complementarity constraints as a nonlinear constraint and hoping SNOP will do its job. Or you can explicitly tell the solver and get a more complete algorithm. The initial version of this algorithm said, let's just use SNOPT. Rely on the fact that if SNOPT is allowed to fail, it'll just mean that sample is temporarily rejected. It will eventually come back and succeed because will have the opportunity to sample from a closer point to the tree, right? So this sort of puts all of our tools together, right? This is the RRT plus trajectory optimization plus sums of squares plus LQR, right? And it, yeah.
For graph reading purposes, what's the goal here?
The goal is the upright, which is now only available via history.
Oh yeah, that's why it made sense before. Okay.
Yeah. I don't actually know. I must have put two different things together. They overlapped each other. Cool. Okay, so what can you say about the algorithm if you put all these things together? There's something really powerful, which is now the notion of coverage, right? So there's this notion of we talked about probabilistic completeness of the RRT, and the thing you'd like to be able to have is probabilistic feedback coverage. You have some set of initial conditions for which it is possible to drive the initial condition to the goal. Others may be unreachable, right? So there are some states of my humanoid that I'm about to face plant, and no amount of control effort in my actuators is going to get me back to the upright, right? So there are some things that are off limits. But of the set of initial conditions which are stabilizable, you'd like to try to cover them with a feedback controller. And this algorithm has the property that, however inefficiently, just like the RRT, it will eventually take any set of the initial conditions, of the stabilizable initial conditions that has measure greater than 0, it will eventually draw a sample from. It will eventually be close enough, given some assumptions about the trajectory optimization being not too bad. It will eventually, be able to connect to the tree, and whenever it connects to the tree, it will come up with a feedback controller that is locally good and will eventually fill the space. So this picture is an example of a toy system for which the sampling interval was that cyan region. The red line is the known. This thing was constructed to have a boundary where we knew where the feasible initial conditions were. Anything below those initial conditions was stabilizable to the red X. Everything above was not stabilizable to the red X. It will drop down ellipsoidal because this was a quadratic Lyapunov function in this particular case, but you could choose higher order Lyapunov functions. It'll drop down more and more of those ellipses in order to approximate that straight line, right, as time goes on. It works for the cart pole. This time, I showed this like at the beginning, when we did the cart pole, and I said, we'll tell you later what's actually going on here. So this is an LQR tree policy. In this case, though, the regions of attraction that we with some of the squares, but we preferred to also to use, a simple, more general thing is to use sampling to compute the regions of attraction. Okay. It's not as good, but it handles more complicated dynamics. So here's a simple idea of simulation-based. So every time I add a new trajectory to my system, I'm going to assume the funnel is ridiculously big, okay? And then every time I run an experiment, I've got some initial conditions, okay, that are I look to execute the policy. I just have to find one of the funnels that says I'm stable. I will stabilize this initial condition. You can impose a total ordering based on some simple heuristics to make sure you don't chatter, okay? But I pick some funnel that it says is good. I start executing it. You can do this in simulation, of course, okay? If it achieves the target, all is well. You leave the funnel alone. If it doesn't achieve the target, you can actually reduce the funnel, okay, based on that sample. And it does a pretty good job of chopping away. You can chop away every point that the system visited. And for instance, if this is the level set of some ellipse, I just drop the value of rho to accommodate that sample being an outlier, okay? You now just run experiments or run simulations, and you can chop this down pretty efficiently, much more efficiently than the Burridge approach, where you're just simulating lots of initial conditions and then guessing. This is like a very efficient way to somehow chop this down, and it plays very well with the space filling algorithm because, again, I will rejection sample by if I get a sample, it claims that it's in the region of one of the controllers. I'll execute that controller. If it failed, now I'll add trajectories to the library, or if it ended up in free space, I'll add trajectories to the library. Right? So it has a lot of the same space-filling properties, but you don't have to worry about sums of squares. And at the time, we did that because we weren't sure how to handle inequality constraints like input saturations and the rails on the cart pole nicely in sums of squares, but that's all been resolved. We could have handled that problem completely with the sums of squares formulation now.
So what are the benefits then of sums of squares actually? Usually the sums of squares offline first anyway, so this is a library, so why don't you sample it in general?
Sums of squares is going to scale to higher dimensions, potentially, and you never know when you're done with the simulation-based, right? So you don't have confidence, but you, in practice, can get close to the same sort of funnels with simulation-based tools. I mean, really, even when I introduced sums of squares compared to sampling, I think the big idea there is, I mean, it's a certificate if you care about that, but just in practice, being able to ask a question for all x efficiently is somehow about scaling. That's the only way to get to dimensions where sampling becomes impossible. Do you have a question?
I just want to clarify, so this is all happening in real time?
This is offline.
Okay.
The goal would be to come up with a feedback controller, which is represented as a tree, much like the RRT tried to pre-compute a tree from the goal, and then at runtime, what you do is you get whatever your current state is, you find one of the funnels that you're currently covered by, and you start executing. So this is an offline design process, and the next slides are about how you make it online.
Yeah, I was just going to say that this seems really cool, but it also seems like it would be really computational, which seems like it could limit the practical usefulness. Just because it has to think for 3 hours before you can walk across the path and stuff. Great.
So you have to ask the question about how do you adapt to a new situation.
Yeah.
For all the tasks we've talked about where the goal is really, I've got a model, I just want to stabilize it. I think this is a good, so then you get philosophical about whether 3 hours is bad. I used to think it's not 3 hours, but I used to think 3 hours was way too much. In fact, I think I've probably hurt myself as a researcher by trying to find solutions that solve in minutes, because then sort of the deep learning people came by and they're willing to train a network for a month on a GPU, and somehow that's okay. I just thought, man, if for the last 10 years I'd given myself a month in a GPU, what would I have done instead, right? And so it's somehow the game's changed now. You're allowed to spend ridiculous amounts of pre-computation. So this is still cheap compared to that stuff. Yeah.
How would this scale to, like, you described many points to one, but many to many potentially? Like, you're considering multiple possible goals. Like, are there efficiencies? Like, does it find use?
So I don't have a great solution for that. That was the obvious paper that we tried to write afterwards, and somehow the any-to-any doesn't. We never had a satisfying solution to that. For the reasons are sort of down in the weeds, but you have to think about cycle. There's some notion of finding cycles and other things, and what does the roadmap mean on a stabilization type problem. I think it could be done, but I don't have a great solution for it. Okay, so what about, so this is the same thing we did for, by the way, this is the rest of the story for the glider, right? So in the same way we did, I showed you this picture before, so that's just as a motivation of TV LQR and sums of squares, but the way we made the glider really robust when I showed you all those examples was that we computed that set of initial conditions, and then we filled the space with those funnels in order to cover a large range of initial conditions. Right, so any one controller was okay, but it wasn't enough for Joe to pick up the plane and throw it, and it always landed at the goal. So lecture 17, and I finally got SWF to run in my browser. Okay, there you go. Oh, look at that. It's like the stupidest video too. But here's an airplane example. So just to say, once the sums of squares stuff was able to accommodate inequality constraints nicely, then you can start doing things like this. So let's say for the unconstrained airplane, executing a particular trim or slight maneuver, the region of attraction, or the funnel looked like that. It's a finite time region. Then at runtime, when you have new constraints, you can then chop down the funnel. The picture looks like this, and know a new, with very little online computation, you can apply it to that. You can apply that funnel library to new initial conditions, right? The picture on how do you stabilize a walking robot works too. You can do the region of attraction using transverse linearization. Now it's a transverse coordinates Lyapunov function that computed the region of attraction of the initial limit cycle. And then how do you design the recovery maneuvers, right? So the nominal limit cycle stabilized with LQR works for only a relatively small set of initial conditions. At some point you have to do something different. Sorry to make Pete's life hard here. You got to do something pretty different to recover. How do you come up with those recovery maneuvers, right? So, I got to do something like this to recover. Well, you find a state that's outside your region of attraction of your initial controller, you design a crazy maneuver, and then you see what are the set of states for which that works, right? And eventually you fill your space with a handful. The claim is that if you've got a good stabilizing back end here, that a small handful of these sort of recovery maneuvers can cover a large part of space. And in practice, that has played out for the systems that we've pushed this on. Doing the version of the sums of squares that works directly with the complementarity constraints allowed us to do better than the hybrid. That was the CompassGate was the hybrid verification. So we talked about the transverse coordinates. We wrote a Lyapunov function of the transverse coordinates, but all of our regions had to line up with the switching surface and had to go through this jump and all that stuff, and it didn't work for lots and lots of contact configurations. But once we were able to do at least limited sums of squares through contact with the complementarity constraints, then we got to do things like perching on a wall and coming up with the region of attraction that works over through contact basically. So the same kind of maneuvers can now the same kind of filling the space can work for systems that make or break contact. And then for the online planning, this was Ani Majumdar's thesis. He showed this sort of this set of tools where you pre-compute enough funnels that are a library of funnels that are, let's say I'm going to go straight, I'm going to bank to the left, I'm bank to the right. He developed the tools to be able to trim the funnels at runtime to account for new constraints. And how do you come up with a sufficiently rich set of those trajectories to fill the space? And he was able to execute high performance maneuvers on a small aircraft in a ridiculously small flight arena, which is our holodeck, right? So everybody's always asked, so why is your plane small or whatever? It's because my room's small, right? So why does your perching trajectory only last 0.8 seconds? Because otherwise we'd hit the wall on the other side. And it's very hard to start these things at speed and do something interesting before you hit the wall. But Ani did it, and with a small plane. So if the obstacles aren't known at runtime, you pre-compute the library of parameterized funnels. You shift. If there's trivial invariance in the dynamics, you can shift them, right? So the airplane's funnel, when I'm starting at x equals this versus x equals this, is a trivial. I only have to compute that once, right? I can just translate the funnel, and then he's got nice algorithms for shifting and composing the funnels at runtime, and was able to sort of pull off some pretty acrobatic maneuvers with provable robustness. This is actually the one where the audio. You get a spin up a crash in the net. That's a net crash. So those obstacles are in motion, but they aren't known for the plane until. If you haven't done it yet, you have to put MIT in your robot videos, right? So, so that, in my mind, was an important piece of work because oftentimes people, there's a sort of stigma that robust control means low performance control, that you tend up trading robustness for performance, right? So oftentimes a controller that is certified to be robust is not doing acrobatics. And this is, I think Ani really pushed the limits there where these are maneuvers that are pretty aggressive, but we still have good certificates saying that they're going to work. The thing that we have not done, and we weren't able to do yet, and Pete was when he came on and started helping with, was that we don't have, as soon as you put perception in the loop, right, then we have no certificates, right? So as soon as if we put bounded uncertainty on the location of the obstacles, fine, we can do that with sums of squares and all our model-based things, that works. If the returns from my perception system, trees may appear, I might just miss trees. The distributions that a perception system actually has, we cannot address currently with these approaches. I consider that a major shortcoming. So I'm totally off script now, but does that idea land? Does that make sense to people? Yeah.
What if you had a model for your perception errors, then could you still use this? Because then it's similar in concept to having uncertainty in your obstacle errors.
So that's exactly what I tried to say. So if the error of my perception system is that I always identify that cup, but I identify its pose plus or minus 3 centimeters, that I can handle. If it's I didn't even see the cup, or I thought I saw a cup, but it actually wasn't a cup, which is the way real vision systems work, then I've got nothing. I think certificates are possible, but we don't have them yet, right? So it requires a different level of, of course, if you never see any, if there's a chance at every frame that you would never see anything, then your only hope is to do something over time. But I think the distributions of uncertainty that I think are representative of perception systems are not yet nicely handled by these techniques.
Can't you get a pretty good approximation if you, so suppose for simplicity that your world only has 5 different kinds of cups and you're only trying to estimate estimate which type of cup it is, and you have some sort of model on your perception system, given that this cup is identified by our perception system, the probability that it actually is this cup is this. And then that's really similar to your Poe's estimation uncertainty. So should we be able to do it if you had this model of given this identification, what the object is, and then that can be tied to the Poe's based off of the volume of the object.
Yes, I think that is within scope. I think if it's, if the pose comes out, but it could be one of 3 different geometries, for instance, then you could ask for a commonly Lyapunov function that works for all 3 of those. If you had a pre-computed library of maneuvers, you could ask which of them is going to work for all, given my current uncertainty. There are probabilistic versions of the sums of squares that give you some probability, some chance constraints. The more of these things you add on, the harder it gets to efficiently solve with sums of squares. But I think those types of uncertainties are within bound. The biggest thing that I don't like about this is that it still depends on full state feedback, right? The notion of trajectories, although now hidden, it's an important point that funnels somehow you can ask about robustness. Even if you use a trajectory which may not be realizable with the real model, you can use that to compute a region in state space, and then ask, will that region still be valid if the model was wrong? So the trajectory sort of disappeared from inside. The trajectory might have had to move, but you can still ask, is this an invariant set for my uncertain system? So you can ask fundamental questions about robustness and uncertainty when you're thinking about regions that you couldn't have asked when you're thinking about trajectories. Okay, so that's good. You can think about state uncertainty, you can think about that. Okay, but the fact that if I'm going to fold a towel, I would have to write the state space of the towel and estimate the full state of the towel in order to decide which of my actions I'm going to run. That's a non-starter. That's just not the right way to think about it. So what I think the pieces that we need to fill in is if I have, first of all, an automatic way to come up with these controllers in the same sort of space-filling way. What was really good about this is that whatever part of state space I knew I couldn't handle yet, I have a principled approach for designing a controller that will now handle that part of state space. The controllers need not be full state feedback controllers, but I don't have an automatic way to generate a reactive controller for each of these individual funnels. That's one major goal. Did I say that clearly enough? Yeah? And then the second thing is, once I have those, an automatic way to sort of generate that, I'd like to be able to project into this. I think it's okay to have this notion of state space at design time, but the overall control techniques should not be wed to the trajectories too tightly, because then even if deciding which state I'm in requires full state feedback, that's also a gotcha. As soon as you have a dependency on full state feedback, it's bad. Yeah. So I think coming up with better controllers, the design for sort of better local controllers means all those funnels get bigger, but it also could reduce the dependence on state estimation. And I think it has to. I think the notion of having to know the full state of the world is just too much. And then the space filling has to accommodate whatever you've done with the better control design. Sorry, did you have another question?
Yeah, so how does this change if instead of trying to plan a trajectory to a specific goal point, your goal is coverage?
So, right, in the forward, the case, it was actually from some set of initial conditions, try to cover as much as possible in the final conditions. And you could do the same sort of, you can imagine the same sort of sampling approach in that case. So the any to any was hard because you have to think about cycles and everything, but if it was really, I've got a final set, I've got an initial set, you can ask about coverage in that and use that as an explicit objective. There's a tension between the size of your inlet of your funnel and the size of your outlet of your funnel. So you have to pick whether you want to be big at the end or big at the beginning, for instance, or which one is explicitly being optimized. But everything you'd like to write down in that space is possible to write down.
But that's still, you have like, your goal could be anywhere in a region, but it's still like one trajectory.
So you would fill the space, so in the simple case, let's say I have an initial condition that's fixed, and I'd like to end up with a set of trajectories that cover this space, right? So I've got one maneuver that sort of gets me here. I sample again, I don't have anything, so I come up with it's just the opposite version of the tree that sort of gets here. Each of these are funnels all the way back. And then if you had a set of initial conditions, typically we just sample here too, but you could try to achieve coverage in both places.
Sure, but like rather than a trajectory of some point in an initial position and some point in a final position, your goal is just to literally cover area.
Oh, I see. You want to do lawn mowing or something?
Yes.
Or, that was probably not the best name for it. I mean, there's there are important scientific problems that require solving that problem. I haven't thought of that. I haven't thought that through, but I would imagine you could try to do something similar. In many cases, there's sort of like the clear thing to think about is stabilization to a point. Many times there's sort of but there's a topological equivalence in sort of problem space of like you can normally somehow convert the problem of coverage or something into like trying to stabilize some point, and that's often the best way for me to think about it. I haven't done that thinking for the lawn mowing. Yeah. Okay, cool. So next week we'll start doing more explicit stochastic and robust control stuff. And then the last set of lectures will be on reinforcement learning. And then I get to hear from you guys about your projects. See you next week.